All right, welcome. This is the AP Physics Force Test Review Solutions. Here we have section 2. These are some practice problems. All right, let's get started. So here's the scenario for the first one. Okay, you could read it if you want. Part A asks is it possible for the block to be slowing down? If so, a possible value of the magnitude of F1 that would allow the block to slow down. If not, explain why not with reference to one of Newton's laws of motion. Okay, so here it's always good practice to label certain things. So here we have this part, which is here we have, see if I can zoom this in. Yeah. Oh, no, I like it like this. Here you have force applied, so this is F1. The theta here, so this is the cosine theta part. Then you have the part that's going up, right? This is F1 sine of theta. Okay. Again, there is a force down. Oops, sorry, let me just change that color. Here you have force of gravity, which is just mg. Then you have force normal. Then you have a force of friction, which is this way. Force of friction, which is just mu n. And n here is, ooh, that's very interesting. There's two parts here. All right, so first thing, okay, is it possible for the object to slow down? Yes, it is. So we would say yes. So the first question, yes, it is possible. Okay, our claim, this is our claim. Our evidence is that if the F net is if the F net is negative, so that means the object can be going this way. Okay, so here's your force. All right, here's your force going down this way. Then there is an opposite force this way. It can be like drag or anything. Here's the other force. This is the opposite force. And let's say the force forward was 100. If the force opposite was 105, so do you see here F net would be equal to 5 negative, okay? Because let's say we treat forward and up as positive. So here then F net would be negative 5n, okay? Therefore, this means the object is slowing down, okay? So all we have to do is try to find a value such that the F net here is negative, okay? So the only forces that you have in this whole scenario, okay? So you could set this up different ways. Here we have, let's see, how am I going to do this? Here, you know what? A lot of people like doing this. A lot of people like setting up F net equals to M, okay? I'm not used to that. Okay, you could do that if you want. So here I have F net is equal to ma. What are my forces here? So force normal cancels out with force gravity. So all I have is my applied force, which is F1 cosine theta. Okay, let me try to color code that so you could see what I'm talking about. Okay, here you have F1 cosine theta. That is your force applied. That is positive. Then what you have here is you have your subtraction of mu n. Mu of n, ooh, this is very tricky. In this case, is just what? Mu of n is not mu of fn. The normal force on the block is 7 newtons minus 1. We have the mu, and then we have normal force, which is just mg. But the normal force here has a component to with f1 sine theta. So it is really here you just want to have this subtract this. You want to have the F1 sine theta. Okay? Because it's going the same direction. So minus down. So this can, okay. So there is a frictional force here. Okay? So what you would do, okay, because you don't even need a numerical answer, is that you want to select. First of all, you can select theta such in a way that there isn't. So let's say theta here was simply 45. Okay, so let theta equals to 35 to just balance things out. You want to let f1 cos let what is cosine of 45? Let's see. What is cosine of 45? No, I don't know. What about cosine of 1? Yeah, let's do that. Let theta be equals to 1. Let's see if there's even a sine part. Oh no, it's 30. We can't change it. Equals to 30. Bummer. Okay, hold on. What's cosine of 30? This is ugly. So here, so it's f1 like times a weird 0.86. Okay, minus mu. Okay, and this is mg. So this is what 7 newtons minus a f1 sine of theta. So that is what 1 sine of 30 sine of 30. Okay, which is this whole thing. Okay, is going to become because I could also make the substitution here. All right, we know that as 0.2. So all this will become 1.3 newtons. So you want to select F1. You want to select F1 zeroth to be greater than 1.3 newtons. Here, you could just divide this over if you want. Okay. Oh, sorry. Okay. So F1 has to be greater than 1.3 divided by 0.86. So you want to have a force applied greater than 1.11 newtons. Let me just round this. Okay. So here you want to understand that yes, it can slow down. You just have to have a force applied that is stronger than the force of friction. And the force applied, make sure it's a large amount because you're only taking the cosine part. Okay. And as you're increasing it, please understand that there's also going to be a sine part. Okay. You never want to have it go past 45 degrees. Okay. So there you go. All right. Part B. In order to double the block's initial speed, 10 meters per second, how much the magnitude of the force applied change? What? This is a trick question. The reason why it's a trick question is you're trying to double the block's initial speed of 10 meters per second. Okay. First of all, you can. Wow. Okay. How must the magnitude of force 1 change? What? So here you have the initial velocity, VI, as 5 meters per second. Now you want a VF to be 10 meters per second. Okay. What you want to do is you want to add a force here. Okay. First of all, this hurts my brain. The reason why you can't do this is that this is a okay. So the units of this is meters per second. This is newtons. Newtons is just kilograms times what is it? Kilogram per meter per second squared. They're different units. You can't combine these. No. So it does not change. This is such a really bad question. Okay, you can't really double the object's initial speed. How much the magnitude of force one change? There's a more complex answer, but here this is a simple answer for physics. You could think about throwing in energy, right? If you threw in energy into here, like you threw in some potential energy, right? You could increase its speed, right? In order to double the block's initial speed, you might want to put it on a ramp. Okay, that could double its initial speed because now it has more gravitational potential. But for the sake of this question, you couldn't. All right. So number two, so that's why it doesn't change. The force can't really change the block's initial speed anyway. Okay. Two, a drag race car speeds up from rest to 22 meters per second squared in 2 seconds. The car has that much mass. The driver has a mass of 80 kilograms. Calculate the acceleration of the drag car. So here, a couple things you want to get. The drag car has both the driver and wait, is it the car? Oh, interesting. Okay, this is very interesting because the acceleration of the drag car. So, okay, so acceleration. Okay, so let's see. Let's calculate the acceleration of the drag car. So a gyration goes from rest. So VI is equal to from rest 0 because it's from rest. VI equals to 0 to here. So that's V final is equal to 22 meters. And time is equal to 2 seconds. The kinematic equation is that acceleration is also defined by your change in velocity over your change in time, which is just simply v final minus vi divided by t final minus ti. But ti equals to 0. So sometimes you just see it as how much time occur. Okay. I hate doing this, but I'm just going to do it. Equal, right? Okay, that's bad. Okay, okay. So V final was 22 minus 0 because it was from rest. Time was 2 seconds. So acceleration was equal to 11 meters per second squared. Okay, there you go. Good. You didn't have to do force. You did not have to do mass. This is just the kinematic equation. Can I give you a side note? Here's an interesting side note here. Okay, remember our equation from kinematics, which is force times no from the Newton's force. F net is equal to mass, but we also know that A is equal to V final minus V initial over T. Technically, right? F net divided by mass is the same thing as V final minus V initial divided by T. So F net can just be defined as velocity final minus velocity initial divided by time multiplied by mass. It gets more interesting. You can distribute the mass over mass times F final minus mass V initial over over distribute that. Okay, is equal to F net. Okay, there should be a T down here. All right. So I'm going to multiply T to the other side. So time plus the force net is equal to mv final minus mv initial. This is the rule of conservation of momentum. momentum. This is your next section. Okay, interesting. It pops out here from the F-net equation. I don't know. That's just something interesting. If you work around with the deviation, you're gonna see a lot of interesting things pop up. Okay. Okay. Sorry. Let's go back to the equation. Calculate the net force of the drag car. Drag car. Okay. Drag car has a net force, so F equals to ma. Mass was here. Drag car. Drag car is just the drag car. Okay, that's just 800. And acceleration was 11. So F is equal to that. Okay, what's 800 times 11? Okay, this becomes 808 8,800 newtons. That's the force net on the drag car. That's equals to F equals to ma. There's no other part. Which experience a greater net force? The wind, the driver, the car, or both the driver and the car experience at the same time. Okay, so this is for the drag car, right? Drag for the drag net force on the drag racer. Wait. Hold on. The drag race mass is 800 kilograms. Yeah. The car, drag racer. Yep. Okay. So, racer. Here's the other thing. But this mass equals times acceleration. If mass here was 80 kilograms times acceleration was 11, it becomes 80 times 11 is 880 newtons. This would be for the driver. This is the mass. So there is more force acting on the drag car, right? The drag race car than it is on the driver. So which experience a greater force? The wind? No. The driver? No. The car would be experiencing it. Okay. The driver and the car experience the same net force. Um, so the car and the driver must experience the same acceleration. That's why. So the A of the system is the same thing as A on the car and A on the driver. When the car changes, okay, to calculate the net force on the driver, we did that here, and with the same acceleration and a smaller force, the driver experienced a smaller net force. We already saw that right here. Okay, so the driver is what experiences a larger net force. Good, because the driver is at 8,800. 3. Can we say anything more about this? No, I'm going to leave it at that. 3. A car slides up a frictionless incline plane. How does the normal force of the incline on the car compare with the weight of the car? A car slides. That's interesting. Can I rotate this? No. Can I rotate this? Yeah. Okay. A car. This is interesting. Here's the car. Let me just draw the car real quick. Here's the car. Here's the car. It drives on a frictionless inclined plane. How does the normal force of the inclined plane compare to the weight of the car? What? Okay, this is a very interesting question. So let's just give its components. This is interesting. So let's see. So we have here so far going down, which is just mg, force of gravity. Then we have its component force. So perpendicular to the surface is the normal force. Then we have the force going down this way, which is just mg cosine theta, right? And we have this part, mg sine of theta. Okay. How does the normal force of the incline of the car compare to the weight of the car? The normal force must be equal to the car's weight. No. The normal force must be less than the car's weight. Whoa. There is a theta here, right? There is a theta here. So let's just make theta 0, okay? Okay. So let's just throw in some numbers here. Let m be equals to 10, okay? So the weight of the car is going to be defined by mg, right? Which is just 10 times 10. So the weight of the person of the weight of the car is 100 newtons, okay? We know that, okay? The normal force is equal to mg cosine theta, right? Because they're opposite force, okay? Normal force is mg, okay, which is the same thing. So 10 times 10 times cosine of what, 30 degrees, okay? 10 times 10 times cosine of 30 degrees, 86. So the normal force is less than the car's weight. Done. Okay? You could throw in any other value here and it's still true. Why is this true? Okay? Please understand that the force of gravity, the mg, is split. So the mg, if you want to think about this conceptually, the force. So hold on here. Let me make this a little bit more clear. So on a horizontal surface, okay, F, G, and N here, okay? They both, so here mg is equal to just mg, right? But once you throw in an incline, the force normal, okay, the force of gravity is split. So this becomes an m. So the mg is split into two parts. Okay, it's split to an mg cosine theta, and there is split into an mg sine of theta. All right. So if this has like 10, this has to be a different value, if that makes sense. So if this is like 100, this has to be separate, okay? Because there's a cosine part and there's a sine part that's in there, okay? So the force is spread apart on the cosine part and the sine part, okay? And I think that's it. Hold on, let's just check. Okay, yeah. So that is just what justifies this idea. The normal force has to be less than the car's weight. Okay, because the weight is greater than the normal force for the incline. Why? Because the weight of the car, right, is a summation of mg cosine theta and mg sine of theta. So mg cosine of theta has to be less than mg. Likewise, mg sine of theta just has to be less than mg as well. Okay? All right, so there you go. Those are all your Section 2 practice problems. Okay? Well,